Oke. Baik, selamat malam semuanya. Hari ini kita akan melanjutkan materi yang kemarin, yaitu browser-based model with TensorFlow.js. Ini yang kedua ya, pertemuan kedua mengenai materi tersebut. Nah, agenda hari ini kita akan bahas tentang TensorFlow.js, converting model JSON, transfer learning with pre-trained model. Nah, sebelum itu mungkin aku mau bahas dulu untuk tugasnya, karena kemarin aku belum sempat bukain tugasnya ya, tapi aku udah set di Google Classroom untuk tugasnya. Kemarin aku udah sempat kasih tahu kalau tugasnya yang minggu ini itu kita cuma ngeringkas gitu. Nah, jadi di sini ada udah aku juga bagi ya link yang ini ke Google Classroom. Jadi ini bisa dibaca-baca lalu diringkas. Semua ini ada yang transfer learning. Di sini juga ada contoh coding juga. Kalau diikuti nanti juga bisa buat latihan. Ini kalau mau add style-nya, habis itu JavaScript-nya. Nanti bisa diikutin semua dari sini. Dan ini akan buat teachable machine learning. Machine, terus di sini nanti bisa di-try. Sini bisa lihat code-nya. Ini glitch-nya. Ada yang mau tanya nggak seputar tugasnya? Ini untuk yang codingannya. Nanti bisa dilihat, klik yang ini, check my complete working code. Nanti akan muncul seperti ini. Ringkas sebanyak 300 sampai 500 kata, nanti dikumpul dalam bentuk PDF. Oke, tugasnya seperti itu. Kalau nggak ada yang mau bertanya tentang tugasnya, kita next ke materinya. Gitu. Oke, baik. Kita lanjut ya ke materinya. Jadi untuk tugasnya udah dikasih semua, udah cukup jelas ya. Sampai ke sini, 17. Oke. Ini untuk tugasnya. Oke, kalau gitu kita lanjut ke materinya. Nah, semuanya udah siap belum nih? Hari ini kita coba-coba yang lainnya gitu. Oke, kita next. Recap, kemarin kita udah belajar ya kalau caranya bikin yang HTML, buka web browser, kayak gimana. Caranya running. Oke, sekarang kita next lagi. Nah, apa itu TensorFlow.js? Kemarin juga sudah ada. TensorFlow.js adalah library machine learning Google untuk JavaScript, dan itu seperti versi asli TensorFlow yang keluar dengan Python. Tapi ditunjukkan untuk orang yang membuat kode dalam JavaScript atau Node.js sebagai gantinya. Oke, ini kita coba lihat videonya. Di sini ada superpower. Oke, superpower with TensorFlow.js. Oke, bentar aku share some.
Hello everyone, I'm Jason Mays, developer advocate for TensorFlow.js here at Google, which basically means if you're using machine learning in JavaScript, there's a good chance our paths will cross. Now today we'll talk about how we can achieve superpowers in the browser with TensorFlow.js, so let's get started. Now the first question you might ask yourself is why would you want to do machine learning in JavaScript in the first place? And JavaScript has many unique selling points to consider here, so let's look at some of those. First, JavaScript enables you to use machine learning anywhere that JavaScript can run, and that includes the browser, server-side, desktop, mobile, and even Internet of Things-based devices. And if we dive into each one of these stacks in more detail, you can see many of the technologies we know and love. On the browser stack, we've got modern web browsers, server-side is driven by Node.js, React Native for mobile native apps, Electron for desktop native apps, and of course Raspberry Pi for IoT. Now JavaScript is one of the only languages that can run across all of these devices without extra plugins being required, giving you the ability to deploy and run anywhere with one code base, and that's very powerful stuff. Now with TensorFlow.js, you can run or retrain via transfer learning or write your own models completely from a blank canvas, just like you can do in Python with the original TensorFlow, but in JavaScript. And with this, you can use it for anything you might dream up. Things like sound recognition, gesture-based interaction, sentiment analysis, conversational AI, and much, much more. Now, there are three main ways we can use TensorFlow.js based on your familiarity with machine learning, JavaScript, or both. And the first way is to use our pre-trained models. These are easy-to-use JavaScript classes that can be used for many common use cases. There are many situations where you don't need to train a brand new model from scratch, and instead you can leverage existing work that exists. So let's take a look at some of those. Here you can see several popular pre-made models available with TensorFlow.js today. Things like object detection, or body segmentation, the act of classifying each pixel in an image to determine if it belongs to a human body or not. Or what about pose estimation to understand where the joints in the human skeleton may actually be? There's various natural language processing models such as sentence encoding or our BERT Q&A model, and many, many more. Let's see some of them in action. First up is object detection. This model is using a model known as Cocoa SSD behind the scenes and is trained on 90 common objects. As such, it can recognize those objects in images and provide us with the location of each object with the bounding box information it also exposes to us, as you can see on the image on the right. Now notice how it can detect multiple objects and multiple classes of objects at the same time. This is different from image recognition, which understands something might be in an image, but it won't tell us where or how many. And this is why Cocoa SSD is super useful. So let's see it in action with a live demo. Now if we flip to the web page that I've created, you can see Cocoa SSD running in the browser. And I can click on any one of these images, like so, and we can see we get real-time classifications coming back. And notice how it recognizes the dog and the bowl and the cup, all different types of objects with high accuracy and the context of where they are in the image. But we can go even better than this. We can enable the webcam and we can see this happening in real time. And here I am talking to you live right now today, and you can see it's recognizing me as a person with 90% confidence, which is pretty damn good. Now, of course, what's really good to note here is not only is this working really fast in the web browser with a high frames per second, it's able to do this all in the browser on the client side, so none of the webcam imagery is being sent to a server for classification. All the inference is happening locally on the client's machine, and that's really useful for privacy because all their data stays on the client machine, which is very top of mind these days. Okay, back to the slides. Now next up we've got Face Mesh. This model is just 3 megabytes in size and has the ability to recognize 468 facial landmarks on the human face. Now not only does this work super robustly, we're starting to see real-world use cases of people using this in production too. On the right-hand side, we see a demo by Modiface, who's part of a L'Oreal group, for AR makeup try-on. In the image on the right, it should be noted that the lady is not actually wearing any lipstick. Instead, this demo uses TensorFlow.js combined with WebGL shaders to augment the chosen color onto the person's lips in real time in the web browser. And let's see Face Mesh in action because it's actually a really cool model, so I want to show you it live today as well. So over to the demo. Okay, so now we can see the demo and you can see Face Mesh running live in the web browser. Now on the left hand side you can see the machine learning in action highlighting on my face where it believes the key points to be. But because this is JavaScript, we can go beyond just doing the raw machine learning and we can combine this with 3D graphics such as 3.js to produce this beautiful point cloud on the right hand side as well, which you can see me dragging around and rotating in real time at the same time as I'm speaking. And you can see how it reacts and updates in much the same way. And JavaScript is very powerful for this kind of stuff. It's been designed for the presentation of information from day one, and it's very, very rich libraries in 3D graphics, data visualization, and so on and so forth, enable you to do this kind of stuff with ease. Now you can also see here that this is running at a good frames per second, around 15 in my browser right now, whilst I'm live streaming at the same time, so do bear that in mind. However, we can actually flip the backends to different forms, such as WebAssembly, to get more performance on the CPU, or we can stay in WebGL to use my graphics card to get better acceleration on that. So it's up to you what environments you want to execute on. Okay, back to the slides. And next up we've got body segmentation. This model can distinguish 24 body areas across multiple bodies all in real time. Now this is really hard to demo live as I need more space in my bedroom, but notice from the image on the right how the bodies of each person are correctly segmented with different colors for different body parts. Now even better, we can get the pose estimation too, those lines in blue, to estimate where the skeleton is, so we can do things like gesture recognition and much more. In fact, with this model, we can be super creative, as we'll see on the next slide. So with a little bit of imagination, we can emulate some of the superpowers we were promised from sci-fi movies. And I'd like to show you some demos today from both myself and the community to show this in action. So first up, invisibility. This is more advanced than simply replacing backgrounds with a static image. For that, you wouldn't even need machine learning. But notice how when I go into the bed still deforms in the image on the right as I move around, or how the laptop screen still plays as I move behind it. Now this prototype uses body pics, which we just spoke about on the previous slides, to calculate where the body is not, so it can eventually learn all the background and keep updating parts where it's safe to do so. Now even better, this whole prototype was made in just one day using our pre-made model and runs entirely in the browser, meaning for many people you can try it out globally even without having any machine learning background. Simply click a link and it just works. No images are sent to the server for classification, leading to real-time results. Or next, what about lasers? Another member of the community from the USA combined his love for WebGL shaders with TensorFlow.js to enable him to shoot lasers from his eyes and mouth, much like Iron Man in the movies. Now this uses the Face Mesh model that we just previously spoke about to run in real time in the browser without issue. And whilst it's a fun demo, you can imagine using this for a movie launch to amplify reach with creative experiences for fans and much more. Or how about teleportation? Combining TensorFlow.js with other emerging web technologies such as WebRTC for real-time communication, A-Frame for web mixed reality, or even 3.js for 3D, we can now create even more beautiful digital experiences such as teleportation to teleport ourselves anywhere in the world in real time. And here you can see me segmenting myself from the bedroom. I then transmit my segmentation anywhere in the world and recreate myself in a different physical location with WebXR. Now remember, all of this is running in the web browser, no app is installed or required to be installed, leading to a frictionless experience for the end user. And having tried this myself, it really feels much more personal than a regular video call, as I can walk up to the person, hear the audio from the right area in the correct direction, and maybe next time I'm presenting to you, I'll be able to do so in your own room like this, as if I was really standing in front of you. And of course, there are many other delightful creations we can make too, beyond just superpowers. How about this clothing size estimator that I created? Here, I've created a tool that can estimate your clothing size in under 15 seconds in the web browser to automatically select for you the correct size of clothing on a website. Now, I don't know about you, but I can never remember my sizes for clothing. And now, with this tool, I can simply enter my height, stand facing the camera, and once to the side, and it can automatically choose for me the correct size of clothing at checkout. And of course, this means less returns and less time wasted overall. This was created in just 2 days and can potentially be used by anyone with a single click at the point of checkout on a website. And even better, this is entirely running in web browser, so user privacy is preserved as no images are sent to the third-party server for classification. And one more example from the community. Here, someone has managed to bring an image of a model from a magazine to life using a combination of WebXR and WebGL. Note, even with these fancy particle effects and machine learning running, this is actually running on a 2-year-old Android device, and still the performance is great. The creator of this piece is currently working on making these avatars speak too, so that's super exciting, and stay tuned for more. Now, the second way you can use TensorFlow.js is via transfer learning. At some point, you're going to outgrow the pre-made models that we've created, and you want to use your own custom data. And transfer learning allows us to take an existing model, use what it's learnt, and then apply similar problems on the same domain to this, such as recognizing a cat instead of a dog, or using the same image recognition model. Now, if you're familiar with machine learning, you can of course do this programmatically in code, but today I want to show you 2 easier ways to get started. Now, first up is Teachable Machine. Now, this is super easy to use and runs entirely in the web browser, both for training and for inference, which is basically the act of using the model to classify something new. Now, the best way to explain this is with a demo, so let's go and try it out. Okay, so now we can see the demo screen, and this is basically on the website called teachablemachine.withgoogle.com. And if you go to that site, you're presented with 3 options here. You can see we've got an image project, an audio project, or a pose project. Today, we're going to go and try and do a custom image project, so let's click on that. Now we're presented with the following screen. We're allowed to add different types of classes on the left-hand side, so let's go ahead and give them some more meaningful names. Today, I'm going to try and recognize my face, so let's put my name here as Jason, along with a deck of playing cards. So let's put the name cards in class 2. And of course, if we wanted to recognize more than this, we can add more classes by clicking the Add Class at the bottom. But now we need to provide some training data. So we click on Webcam and allow access, and now we get a live preview from the webcam. And here, I can simply add some recordings of my face at different angles and rotations to give it some variety to understand what a Jason face actually looks like. So let's do that right now. Okay, so I've got about 38 images of me moving my head around, which is enough for this exercise. We're now going to do the same thing for cards, and you can see here I've got a deck of playing cards that I'm going to bring to the screen and do a similar thing. And it's important to get roughly the same number of images to avoid any bias. So I've got 42 versus 38, that's close enough. So now we can click on Train Model, and what's going to happen now is live in the web browser, it's going to retrain the top layers to attempt to classify the differences between the training data I presented to it. And you can see in just under 30 seconds, it's already come back with a live trained model, and it's currently predicting Jason on the output here, as you can see on the bottom right. If I bring the cards into view, it says cards, and Jason, cards, Jason, cards. And you can see how fast and responsive that is. Now, if this is good enough for what your needs are, you can actually click on Export Model at the top right here, and click on Download, and you can download the resulting TensorFlow.js model files that you can then use on any website you wish to then do something useful with. So maybe you can control some animation when it spots a cat in your room or something like this, or send you an alert, or whatever you wanted to do, it's completely up to you. Okay, back to the slides. Now, Teachable Machine is great for prototypes, but if you want to launch a production model with gigabytes of training data, then maybe Cloud AutoML can be used for this instead. It even supports exporting to TensorFlow.js. In this example, we can see someone trying to classify flowers. All they've done is uploaded the folders of flowers to Google Cloud Storage, and then we can move on to the next step of the training process. In the next step, we can see how the user can now select if they want to train for higher accuracy or faster prediction times. Of course, there's usually a trade-off between the two, so you can select your preference at this point. You then simply set your budget and continue to allow the model to train, and at the end, it will give you the option to download. And you can see here, once complete, you can now export to TensorFlow.js as shown. Simply download the files and host on your website or content delivery network. You now may be wondering, how hard is it to use this model that you've just generated in TensorFlow.js? Well, actually it's pretty easy. In fact, it's so easy it fits onto a single slide. Let me walk you through this. First, at the top, we've got two HTML script imports. The first one is for the TensorFlow.js library, and the second one is for the Cloud AutoML library. Next, we have an image tag for a new image that we want to classify. In this case, I grabbed an image from the internet, a daisy, but it could be anything. It could even be an image from a webcam stream if you wanted. And then finally, we have the actual JavaScript code, but it's actually just 3 lines of JS to do the hard work. The first line, we simply call await tf.automl.load image classification and pass to it the location of our machine learning model that we trained. In this case, it's called model.json and is located in the same directory. This is the file we downloaded in the previous step and is simply hosted somewhere on your web server. We then use the await keyword here because the model load is asynchronous, meaning that it takes some time to complete. This allows us to wait for this to finish before continuing sequentially. Now once a model is loaded, we can then grab a reference to the image we want to classify using document.getElementById and pass the ID of the element we wish to use. In this case, it's the daisy image, which represents the image tag above, as you can see on the top here. Now finally, we can call await model.classify and pass to it the image we want to classify. Again, depending on the model, this can take several milliseconds to execute, so this always uses the await keyword too. And then you'll get a JSON object returned to our predictions constant, which we can then loop through and print the results or do something useful with. It should also be noted that you can call model.classify as many times as you like with different images once the model is loaded, which is how we can achieve webcam detection in real time. Now finally, the third way to use TensorFlow.js is to write your own models from a blank canvas. Now of course, to give a tutorial on this would require a whole new talk, so today we're going to focus on why you might want to consider doing this in JavaScript and the benefits you can get if you choose to do so. First, let's start by explaining the TensorFlow.js architecture. We've got two APIs. We have a high-level API known as the Layers API, which is very similar to Keras if you're using Python already. In fact, if you know Keras, you'll feel very comfortable with our Layers API. Next, we've got a low-level API known as the Ops API, which is more mathematical in nature and allows you to do things like linear algebra and so on and so forth. This is similar to the original TensorFlow API. So let's see how these come together. Here you can see how our pre-made model sits upon the Layers API, which itself is sitting above the Core or Ops API. Now, this lower level API can speak to many different environments, such as the client side, which includes things like the web browser, for example. Each one of these environments can execute on a number of different backends. For example, the CPU, which is always available. But we've also got WebGL for GPU acceleration if it's supported, or WebAssembly, or WASM for short, if supported for faster performance on CPUs. And there's a similar story for server-side environments via Node.js too. Note here that our Node.js implementation can talk to the same TF-CPU and TF-GPU bindings that Python TensorFlow talks to. So yes, that means we can get the same or better performance as Python for model inference with the same CUDA and AVX support, as we'll see in a few slides' time. Now, if you do prefer to use Python for your machine learning research, you can still continue to do so using Keras models and TensorFlow Safe models in Node.js without conversion by loading them directly with our Layers and Ops API accordingly. And this is great as it allows you to integrate with web teams who are highly likely using Node.js, allowing you to then make your model available to the world with the reach and scale of the web. And even better, if you want to convert your TensorFlow saved model to run in the web browser directly on the client side, you can use our command line converter to do this as long as the ops are supported by TensorFlow.js on our client-side implementation. Now this will convert the saved model to the JSON format required so the model on the client side can run in the web browser. And let's talk about performance. Here you can see for MobileNet v2 running on GPU and CPU on Python and in Node.js. And as you can see, the GPU has a very negligible performance difference between Python and JS. In fact, I think it's like less than 1 millisecond there. So within margin of error, essentially. For all intents and purposes, this is basically the same result. However, it gets much more interesting when you attempt to consider more than just the inference times. Typically, an ML model requires pre- and post-processing code as well. And if you convert this code to be in Node.js, we see much faster performance in Node for some architectures as shown on the next slide. And here we can see how Hugging Face, who are very popular for natural language processing models, managed to convert their Distilbert implementation into a full Node.js one for the pre- and post-processing layers. This led to a 2 times speed boost for full end-to-end results, which is just one reason you might want to consider using Node.js too. And this is made possible due to the just-in-time compiler that JavaScript has that optimizes code at runtime and is a unique feature to JavaScript. So now let's talk about client-side superpowers that can actually only be achieved by running in the web browser. Now the first is privacy. Inference is performed on the client machine, so that means no data is ever sent to third-party servers, maintaining data privacy for the end user. This is particularly important for medical or the legal industries, where it might be a requirement not to transfer the user data to third parties. And there's growing concerns around privacy these days, so with TensorFlow.js you get it for free. Next up is lower latency. As JavaScript has direct access to the sensors on the device, such as the microphone, the cam, accelerometer, and much more, there's no round-trip time from the server to the client and back again. Latency could be close to 100 milliseconds or more if you're using a mobile connection. Assuming zero latency for processing and inference, the maximum FPS caps out at 10 frames per second if you're sending images one by one, which is less than ideal. With TensorFlow.js running on device, we can go much faster than that, of course. Next up is cost. If you're not sending data to the server, then of course we can save on costs on the hired CPUs, GPUs, and RAM that we might be needing otherwise on the server side. And assuming you need to fire up just 10 high memory machines with a GPU, you can easily be hitting an additional $60,000 per year. And as there's no server, you can just pay for the model hosting and website assets, which is far cheaper than running an ML server. And then finally, here are some benefits to using Node.js. We can use the TensorFlow saved model format as discussed without conversion, and of course this is compatible with TensorFlow and Keras models. We can run larger models than on the client side. I believe there's some limitations due to GPU memory limits and so on and so forth that limit the upper bounds of the size of models you can run in the web browser. And with Node.js, we can leverage the full power of the server hardware just like Python can. It also allows us to code in just one language, and this is great for code reuse across the stack. And if your existing developers already know JavaScript, which currently 67% of devs choose to use JavaScript in production according to the Stack Overflow survey of 2020, that is a great win for you too. And Node.js itself was the most popular choice by developers in that same survey for frameworks and libraries, with over 50% of respondents using it. And JavaScript, of course, is the world's most used language right now. There's a huge community and support for this if you choose to do so. And then finally, we have performance. It takes the same C bindings, just like Python has, so you've got the same CUDA acceleration and AVX support on the GPU and CPU respectively. And due to the just-in-time compiler in JavaScript, you get that boost if you're doing a lot of pre- and post-processing too, which you wouldn't get in the Python land. So finally, we're going to wrap up with some resources for you to get started if you want to continue your TensorFlow.js journey. If there's one slide you should bookmark and share with folk, let it be this one. This slide has all the resources you need to get started. Our website and API are available on tensorflow.org/js, and our models are also available to use on that same website. Now today we just covered 3 of them. There is actually many more to be used too, so do go check that out. We're fully open source, so do look on GitHub, and we welcome contributions. And for more technical questions, check out our Google group. We also got lots of boilerplate code showing how easy it is to use our pre-made models in minutes over on CodePen and glitch.com. And finally, if you're looking for an all-in-one book, Deep Learning with JavaScript by Manning Productions was written by folk on our team and takes you from zero to ML Hero in just a few chapters. And as long as you know JavaScript, that's all you need to get started. So finally, a quick shout out to our community.
Oke, ini tadi contoh yang pertama tadi sempat yang kemarin ya, common object in context kayak yang kemarin kita sempat tonton gitu. Terus tadi ada yang teachable machine, itu kayak yang tugasnya juga yang kita besok dibaca, tugas itu juga tentang teachable machine gitu. Oke, kita lanjut. Nah, ini ada contoh the next generation website. Di sini ada kayak gambar kita pakai web browser, kita pakai webcam. Terus nanti ini setiap kali kita gerakin kameranya, gambarnya itu juga gerak gitu. Karakternya itu juga gerak, jadi gerak di sebelah. Kita bisa lihat posisi di sebelah-sebelahnya dia itu apa aja gitu. Sama kayak kita gerakin kameranya kita gitu. Untuk yang ini akan gerak sesuai gerakan kita juga. Gitu juga yang ini ya, ini juga sama geraknya sesuai sama gerakan yang kita lakuin. Di sini juga bisa ngerubah wajahnya jadi kayak bentuk karakter yang dia mau, jadi kayak udah bikin avatar sendiri gitu. Oke, kita next. Oke, kita lanjut untuk machine learning in JavaScript. Nah, gimana cara kerjanya? Itu yang pertama run existing model. Kita di sini run existing model, terus kita retrain existing modelnya, baru kita develop with JavaScript. Gitu. Oke, kita coba buka ini. Oke, kayak gini ya. Nah, kita coba lihat demonya. Di sini kita coba pilih dua ya. Kita ambil yang webcam controller yang untuk Pacman ini dulu. Oke, di sini kita bisa coba live. Oke, kita masih loading. Oke, jadi kalau di sini kita diminta buat foto dulu gambar yang kita mau tentuin. Kalau kita yang atas itu, jadi kalau kita ngadep ke atas atau kita foto apapun yang kita masukin di sini itu akan gerak seperti itu gitu. Jadi kita coba ya. Oke, add. Kemiringan nanti nggak bisa ngeliat. Oke, terus yang bawah. Oke, baru setelah itu kita train. Oke, training. Nah, ini udah muncul ya. Kita bisa play langsung di sini. Jadi geraknya sesuai kayak yang ada di foto ya. Nah, seperti ini. Oke, contohnya kayak gitu. Jadi bisa geraknya kayak gitu ya. Ini lumayan gambarnya karena deket-deket ya. Bisa dicontoh gambar yang lebih, nanti lebih mudah terbaca gitu ya, contoh fotonya. Oke, ini mungkin aku kirim juga ke chat buat bisa dieksplor juga sama teman-teman. Oke, jadi kayak gitu. Ini kita juga sebenarnya bisa lihat codingan yang udah jadi gitu ya. Bisa misal kita mau lihat nih hasil codingannya untuk dapat output kayak gini tuh gimana gitu ya. Ini kita bisa lihat di sini. Kurang lebih hampir sama kayak yang kemarin. Ini ada TensorFlow dataset. Ini datasetnya dimana nanti dia tuh cuma nyimpen gambar nih. Dia akan keep example-nya. Jadi hanya di keep sesaat aja example-nya. Terus kalau tadi dari yang ini tuh, kalau di sini nggak bisa di-download. Oke, ini buat training ulang. Berarti di sini nggak bisa di-download lagi model yang udah kita buat. Ini kita bisa tentuin, udah ada ketentuannya. Batch size juga bisa kita tentuin. Epoch juga ada pilihannya 10, 20, dan 40 aja. Hidden unit. Nah, kalau kemarin waktu kita contoh yang rock, paper, scissors, box, sama lizard, itu bisa di-download gitu ya. Kalau yang ini nggak bisa di-download modelnya. Jadi ini sama, ini simpan, nge-keep example-nya sesaat aja untuk data controller dataset, itu keep sesaat, terus oke, di sini webcam-nya pakai transfer learning. Ini lihat webcam, ini karena JSON, ini JSON ya. JavaScript ini. Lihat webcam, controller, pakai mobile net, get layer. Oke, ini nanti bisa dieksplor juga. Jadi banyak banget tadi demonya bisa dilihat. Ini get image, webcam capture, karena tadi di foto cuma sekali aja gitu ya, capture. Kita train capture yang udah ada, training. Ini ada UI, train status, training, predicting, false. Oke, ini terus kalau yang sampel. Ini untuk UI-nya, CSS, nah yang dipanggil ini biasanya HTML-nya. Ini HTML-nya. Kalau kemarin, susunan yang kemarin itu kayak dibikinin case-case gitu ya, case 1, case 2, case 3, berdasarkan kayak rock, paper, scissors. Kalau yang ini, karena dia udah ada satu lokasi yang kayak image sendiri-sendiri gini, jadi dia kayak bikin ini ya, satu div sendiri, panel buat yang top, buat yang right, ini ada yang top, terus center, right, left, gitu ya. Ini bisa diekspor juga codingannya, bisa diperbarui juga. Kalau gambarnya cuma satu tadi, waktu kita coba jalanin, waktu sedikit gini, waktu kita sambil mau lihat layar kan harus lurus gini ya. Itu kayak susah jalannya. Mungkin nanti contoh fotonya itu bisa diubah lagi yang lain yang nggak buat kita kesulitan buat ngelihat layarnya gitu. Bisa dicoba-coba sendiri nanti. Ya, jangan terlalu minggir. Tuh, terus kita coba lihat demo yang lain ya. Aku close yang ini dulu, yang Pacman. Tadi kita udah lihat demo yang teachable machine learning. Kita coba ekspor demo ini. Oke. Kalau kita pakai yang post lumayan susah ya, karena harus rada jauh gitu dari posisi webcamnya. Kalau yang audio ini based on 1 second long sound from file or your microphone. Oke, kalau yang tadi ini kita udah dicoba ya waktu di video. Kita mau coba ulang atau kita mau coba yang audio nih? Kita coba yang audio ya. Ya, audio kayaknya seru, tapi oke, bentar. Background noise. Oke, caranya berarti kelas 2. Oke. Oke, masih lumayan error ya. Bentar ya. Kalau nanti aku isi suaraku semua, tetap kayaknya susah ya. Nyanyi, nggak bisa, nggak bisa. Nggak bisa. Kalau ada yang mau volunteer nyanyi, boleh loh. Kita coba jalanin ini gitu. Harusnya bisa ya? Dia langsung, kayaknya bisa ya. Bisa deh, aku login lewat HP. Jadi nanti bisa dengerin suaranya gitu. Gimana, ada yang mau volunteer? Suara binatang. Ntar, aku bingung nih jadian. Oke, oke, aku cari dulu ya. Aku mungkin cari di YouTube dulu suara binatang buat kita. Aku nyalain mic nanti ya. Oke. Oh, ini nggak bisa diganti ya namanya. Cuma yang bawah yang bisa. Oke, kita kucing sama ya, aku coba ya. Kurang keras. Bentar. Oke, record. Oke, ke record extract sample ya. Oke. Kita coba yang kucing ya. Oke. Kita training. Harusnya ini kalau kayak suara langsung gitu bisa ya. Tadi yang background noise ini 20 pertama itu suara kuku. Yang bawah itu suara kucing. Uh, Tadi yang atas gak kayak suara guguk ya, emang? Oh, oke. Kita coba lihat ya, mesinnya paham nggak ya? Oke, masih training. Oke, masih loading training. Kalau coba inspect kelihatan progress-nya. Oke, kita coba ya. Kok aku pakai F, ini nggak mau langsung keluar ya inspect-nya. Oke. Kelihatannya tadi. Aku belum suara ya, tapi oke. Enggak sih, yang ini guguk sih yang barusan nih. Yang suara kedua ini. Oh iya ya, modelnya rada bingung ya kayaknya ya. Hampir sama ya. Oke. Oke, guguknya kurang guguk. Oke. Lagi anteng dia, jadi nggak bisa. Oke, kita ekstrak sampel baru ya. Tapi yang lebih. Ini pertama guguk benar. Oke, bisa ya berarti ya, kayak gitu. Oke, itu contoh yang teachable machine ya. Untuk yang tadi kan masih ada satu tuh teachable machine yang belum dicoba yang pose gitu ya, kayak kelihatan gerakannya itu bisa dicoba sendiri ya nanti. Ini udah lip sync by YouTube. Oke. Ini masih ada banyak, ada move mirror, performance RNN, ini real time piano performance by neural network. Ini ada Node.js pitch prediction, classify baseball pitch type using Node.js, yang ini visualize model training. See how to visualize in browser training and model behavior and training using. Oke. Oke, example digit. Bisa dicoba-coba semua, bisa langsung didemoin sih kayaknya ini. Ekspor demo langsung bisa ini. Ya, sini bisa sih. Baik. Aku kira ini nggak bisa langsung dieksplor. Kemarin kalau buka harus GitHub kan, kayak yang tadi aku buka GitHub baru bisa dapat link explore-nya. Ternyata tadi ada yang langsung buat dieksplor gitu. Nggak bisa dari loading ini. Lumayan lama ya. Mungkin mau lihat code-nya aja deh. Kalau gitu, aku belum lihat sih yang ini akan kayak apa. Oke, berarti kalau dia lihat di webcam atau di mobile cam-nya kita, itu show you emoji, and you have to find this object in the real world before your time runs out. Ya, nanti ada misal ada emoji yang ini ya, jam waker, kita harus cari sebelum time out gitu ya. Ya ini seru sih kayaknya. Aku penasaran kalau kayak gini berarti dia cuma training apa sama initial emoji. GPU langsung. Oke, ini berarti nanti yang bisa keluar ini ya, kimono, truck, gondola, tennis ball, wig. Ini emojinya. Ini contoh emojinya nanti yang bakalan ditampilin. Berarti dia harus menyamakan yang ada di webcam itu yang kita pegang real itu sama emojinya gitu ya. Itu sama atau enggak. Mention array audio. Pakai mobile net. Oke, ini seru juga ya. Ini beda kayak yang dua contoh yang kayak Pac-Man sama yang rock paper scissors itu kan kita kayak ada dataset yang buat kita simpen, kita keep gambarnya gitu jadi dataset sementara. Kalau ini kan nggak ada kayak kita keep gambarnya dulu jadi dataset sementara gitu. Di ini udah ada gambar emojinya banyak banget tadi. Terus kita nanti akan pegang item yang sesuai emoji itu tampilin. Habis itu ada waktunya, terus itu sesuai enggak gitu. Kita harus cari gambar yang sesuai sama emoji yang keluar di layar kita. Kayak gitu yang ini. Seru juga sih ini. Ini banyak ya tadi. Oke. Yang lip sync ini juga boleh ini dicoba nanti. Buat yang jago nyanyi boleh banget. Oke, kita next ya. Sebelum next ya, sampai di sini ada yang mau tanya nggak? Gimana nih? Ada yang mau tanya sampai di sini? Jadi kalau model-model yang udah jadi tadi kita ekstrak, kita save modelnya, kita pakai, terus kita bisa juga jadiin itu pre-train model gitu ya. Terus kita tambahin kelas lagi yang lain gitu, itu juga bisa. Oke, belum ada yang mau tanya nih sampai di sini. Kita next kalau gitu. Oke, sini kenapa sih perform machine learning itu kita pakai JavaScript gitu. Jadi kan TensorFlow.js ini kenapa sih kok pakai JavaScript gitu? Nah, yang pertama itu karena memungkinkan lebih banyak developer itu menggunakan machine learning tanpa harus mempelajari bahasa baru. Karena sekitar 70% developer menggunakan JavaScript untuk industri. Jadi karena mereka emang udah biasa pakai JavaScript, Node.js gitu ya, udah biasa pakai itu, mereka nggak perlu harus belajar Python untuk pakai TensorFlow ini. Jadi ada TensorFlow.js. Terus developer dapat menggunakan kreativitas mereka di lebih banyak tempat daripada sebelumnya karena JavaScript dapat berjalan hampir di mana aja. Tadi setelah dilihat beberapa demonya itu banyak banget ya, kayak kreatif banget gitu. Ada yang kayak game yang harus nunjukin tadi emoji, terus ada yang teachable machine. Habis itu juga ada yang Pac-Man tadi. Jadi dari Pac-Man pun kan game yang udah ada ya dulu. Terus kreativitas sendiri, jadi tanpa kita harus ngeklik, kita bisa jalanin playernya kita gitu ya. Jadi kita bisa jalanin itu tanpa harus klik, jadi cuma dari kamera aja. Itu juga kreativitas kan. Terus yang terakhir dari sisi klien di browser ke sisi server melalui Node.js, aplikasi asli seperti seluler ke desktop asli, dan bahkan ke perangkat IoT seperti Raspberry Pi. JavaScript merupakan satu-satunya bahasa yang memiliki fleksibilitas eksekusi ini. Jadi dianggap kalau pakai JavaScript itu jauh lebih fleksibel gitu ya selama ini daripada yang lainnya. Makanya ada TensorFlow JavaScript gitu. Nah, ini contoh TensorFlow.js project. Ini ada contoh visualize 3D object. Nah, yang kayak gini ya nih. Ini benar-benar kelihatan 3D-nya nih. Ini smooth banget gitu ya 3D-nya. Kelihatan banget nih. Terus yang selanjutnya, machine learning generate performance or pose of human body. Nah nih, kelihatan kayak, misal ini ada satu aplikasi, kayak kita untuk olahraga gitu ya, kita yang pemula belum pernah ngelakuin workout sendiri, terus di sini kita bisa ketahuan nih, squatnya yang kaki kiri udah 3 kali, yang kaki kanan 1 kali, gitu juga bisa. Terus ini juga nih, ini gesture move. Ini yang performance pose yang untuk ini ya, yang human body ya nih. Terus untuk yang gesture move, to move something in website, itu kayak kita kalau ada website nih, terus kita gerakin tangan kita ke arah sesuai anak panahnya gitu ya. Kita geserin, nah nanti webnya itu gerak sendiri ke pindah page lain gitu. Terus object detection on maps. Jadi kalau di sini ada Google Maps gitu, terus kita ini pointer kita gitu ya, yang hijau ini. Terus kita klik di sini. Nah, nanti dia langsung kelihatan di sini nih kameranya. Jadi kita mau foto apa yang kita klik di sini. Nih. Nah, kalau dia mau foto bagiannya lain, misal dia mau lihat di bagian yang pohon itu, atau dia mau lihat di bagian mobil yang di sebelah sini, itu juga bisa tinggal diklik aja. Gitu, itu banyak banget masih yang contoh yang lainnya ya. Kayak di game basket, jadi kayak kita main basketnya gimana gitu, itu juga ada contohnya. Jadi kayak perkembangannya itu makin pesat gitu ya. Dengan adanya TensorFlow.js ini, selama ini kan industri pakai JavaScript. Terus adanya TensorFlow.js ini bisa ngeubah jadi lebih gampang, kita mau mainin kayak gimana aja gitu. Kita bisa explore kreatif kita mau kemana aja arahnya gitu. Oke, kita next. Nah ini, transfer learning in JavaScript.
Welcome to the TensorFlow.js workshop for Google I/O 2022. In this workshop, you'll learn how to create your very own simplified version of the popular Teachable Machine website to perform transfer learning with machine learning in JavaScript in the browser to recognize any object you desire. But what is this Teachable Machine website I speak of? Let's take a quick look at it in action.
People are training computers and creating machine learning models to explore all kinds of new ideas. New ways to interact.
Yes.
To understand the world. To play. And experiment. But machine learning is pretty intimidating to get into. So we've been wondering, What if it wasn't? With Teachable Machine, we set out to make it easier for anyone to create machine learning models without needing to write any machine learning code. When it first launched in 2017, it allowed everyone to get a feeling for what machine learning is all about. But now, Teachable Machine puts the power of machine learning in your hands, allowing you to save your models and use them in your own projects.
So let's say you want to build a model to recognize you versus your dog. You just open up the site, record samples of you and samples of your dog. Click Train, and you instantly have your own machine learning model, which you can use in your sites, apps, and more. You can upload your model to host it online, or download it to work entirely on device.
With Teachable Machine, you can create custom models for all sorts of things. Using images, audio, or even poses. Personalized machine learning models for the things that matter to you. And folks have already been trying it out, using Teachable Machine in their own experiments, solving problems in their communities, or even just at home. Start creating and see where your ideas take you at g.co/teachable machine.
Great! Now you know the end goal, it's time to open up my code lab that you'll use today to follow along. Head on over to codelabs.developers.google.com in a new browser window. And once the website's opened, search for TensorFlow.js Teachable Machine via the search box. You should then find a result titled Make Your Own Teachable Machine with TensorFlow.js in JavaScript as shown. Click on that. On the page that loads, you'll then see the sections of this workshop on the left, which you can use to follow along as I walk you through them live in this workshop video. So head on to step 2 as I teach you what TensorFlow.js is all about. So first off, what is TensorFlow.js? Well, if you're new to WebML, TensorFlow.js is Google's machine learning library for JavaScript, and it's just like the original version of TensorFlow that came out in Python, but is aimed at folk who code in JavaScript or Node.js instead. This allows more developers to use machine learning without having to learn a new language, and use their creations in even more places than before, as JavaScript can run pretty much anywhere. From client-side to server-side, mobile native to desktop native, and even IoT devices like a Raspberry Pi, JavaScript is one of the few languages that can run in all of these locations without any additional dependencies. And currently, over 68% of professional developers use JavaScript in production. All of these users can potentially benefit from adding machine learning models to their web applications. And what are those benefits? Well, by running in the browser, you can achieve privacy as no sensor data needs to be sent to the cloud. Or how about lower latency for real-time performance with direct access to the device? And of course, lower costs as fewer server-side resources need to be kept running. You also get zero install for a frictionless end-user experience. You can use any of our demos in just one click of a link and reach an audience of billions instantly with no complex environment setup in a way people can share with ease. And if you're new to machine learning, we've just launched a brand new course for web and creative folk who are new to this industry but familiar with web technologies. Here you can go from zero to hero with machine learning in JavaScript and bring your creative ideas to life with TensorFlow.js. This course will teach you how to use machine learning in the browser to create next-generation web apps with superpowers from object recognition to text understanding and more. If you find this workshop too advanced, start with this course instead, and you can enroll today for free using the link on this slide and go at your own pace. But for those of you who already use TensorFlow.js, let's demystify the process of transfer learning so we can make our very own teachable machine. Now head on to step 3 of the code lab. In its essence, transfer learning is all about taking the knowledge that's already been learnt to help learn a different but similar thing. And if you think about it, we as humans do this all the time. You have a lifetime of experiences contained in your brain that you can use to help recognize things you've never seen before. Take this willow tree for example. Depending where you are in the world, there's a chance you may have not seen this type of tree before. Yet, if I ask you to now tell me if there are any willow trees in this image, you can probably spot them pretty fast, even though they're at a different angle and slightly different to the one I originally showed you. Essentially, you already have a bunch of neurons that know how to identify tree-like objects and other neurons that are good at finding long straight lines. So you can reuse that knowledge to then classify a willow tree pretty fast, which is basically a tree-like object that has lots of long, liney branches in the vertical direction. So in a similar manner, if you have a machine learning model that's already trained on some domain like recognizing images, you can reuse it to perform a different but related task. In this case, you can do the same with an advanced model like MobileNet shown here. MobileNet is a very popular research model that's able to perform image recognition on 1,000 different object types. From dogs to cars, it was trained on a huge dataset known as ImageNet that has millions of labeled images. In fact, you can see in this animation here the huge number of layers it has in this MobileNet v1 model. Now, during its training, it's already learned how to extract common features that matter for all of those 1,000 objects, and many of the lower level features it uses to identify such objects can be useful to detect new objects it's never seen before too. After all, everything is ultimately just a combination of lines, textures, and shapes. Now, if you could separate the pre-trained lower level layers of an existing trained model shown on the left from the classification layers near the end of the model shown on the right, which are sometimes referred to as the classification head of the model, you could then use these lower level layers to produce output features for any given image based on the original data it was trained on. Now, assuming the new thing you're trying to recognize can also make use of such output features, there is a good chance they can be reused for a new purpose. In the diagram shown, this hypothetical model was trained on digits, so maybe what's learnt about digits can also be applied to letters like A, B, and C too. So now you could add a new classification head that's trying to predict A, B, or C instead, as shown. In this instance, the lower level layers are frozen and are not trained. Only the new classification head will update itself to learn from the features provided from the pre-trained chopped up model on the left. The act of doing this is known as transfer learning, and that's what Teachable Machine does behind the scenes that you saw in action at the start of the workshop. You can also see that by only having to train the last few layers at the very end of a network, it will train much faster than if you had to train the whole model from scratch. So how can you get your hands on subparts of a model? Head on to step 4 of the code lab. Well, for more advanced research models like MobileNet, if you head on over to TensorFlow Hub at tfhub.dev and then filter for models suitable for TensorFlow.js that use a MobileNet v3 architecture, you'll find results like the ones shown on the slide. Now, some of these results are of type image classification, and others are of type image feature vector as shown. These image feature vector results are essentially the pre-chopped up versions of MobileNet that you can use to get the image feature vectors instead of the final classification. Models like this are often called base models, which you can then use to perform transfer learning. If you open up the page for one of these feature vector MobileNet v3 models, you can see from the JavaScript documentation that it's in the form of a graph model. It should be noted that if you find a model in the layers format instead of the graph format, you can choose which layers to freeze and which to unfreeze for training, which can give you even more options to fine-tune the model further. But what are the advantages of using transfer learning instead of training the whole model architecture from zero? Well, first, time of training is a key advantage of using a transfer learning approach, as you already have a trained base model to build upon. Secondly, you can get away with showing far fewer examples of the new thing you're trying to classify due to the prior training that's already taken place. This is really great if you've got limited time and resources to gather example data of the thing you want to classify and need to make a prototype quickly before gathering more training data to make it more robust. As such, given the need for less data and the speed of training a smaller network, transfer learning is less resource intensive, which makes it very suitable for the browser environment too, taking just tens of seconds on a modern machine instead of hours, days, or weeks for full model training. Alright, now you know the essence of what transfer learning is, it's time to create your very own version of Teachable Machine. Let's get started. Head on to step 5 of the code lab. Now head to glitch.com and open the TensorFlow.js boilerplate page by the link shown on the slide. Once loaded, fork a new copy of that you'll use to implement this project. You'll need to be signed into Glitch if you want to save your progress. Feel free to pause the video to do that and then continue. Now head on to step 6 of the code lab. In this section, you'll be replacing code in index.html. Go ahead and open that up and then replace the contents with the code on the following slides. The only part of index.html that you'll need to update is the content contained within the body tags as shown. Let's walk through the code. First, you'll add a heading and a paragraph tag with ID of status. This is where you'll print the information as you use different parts of a system to view the outputs. Next, a video element with ID of webcam is defined, to which you'll render the webcam later on. Moving further down the code, you can now define some buttons. The first with ID of enable cam will enable the web camera. The buttons with class data collector will allow you to gather example images for your classes of data. The code you write later will be designed such that you can add any number of these buttons and they'll work automatically as intended. Note that these buttons also have a special user-defined attribute called data-1hot with an integer value starting from 0 for the first class. This is the numerical index you'll use to represent a certain class's data by, as machine learning models like MobileNet must work with numbers and not strings. You can then use these numbers to encode the output classes correctly with a numerical representation instead of a string. There's also a data-name attribute that contains the human-readable name for this class, allowing you to provide a more meaningful name to the user to see instead of the numerical index value from the 1hot encoding. Next, you have a button to start training with an ID of train and a reset button with ID of reset that will clear all data so you can start over. Finally, you've got two script imports, one for TensorFlow.js and the other for your script.js that you'll define shortly. If you want to copy and paste the code directly, the completed index.html file is available at the URL shown. Now head on to step 7 of the code lab. Next, you can place contents in style.css to add style to your HTML elements. Here, some styles are added to position and size elements correctly. Nothing too special. You could certainly add to this later to make an even better UX like you saw in the Teachable Machine video. Again, if you want to copy the styles directly, the URL provided has a complete version of style.css to save time. Now, assuming you copied the HTML and CSS correctly, your live preview will now look like this, which contains the bare minimum user interface elements to make your very own Teachable Machine. Remember, after you complete this workshop, you may want to update the code to make the UX even better using your regular web engineering and design skills. Now head on to step 8 of the code lab. Okay, so next it's time to write the JavaScript code that will be contained within script.js. Go ahead, open that up and copy the code on the following slides as you go along. First, start by adding some key constants that you'll use throughout the app at the start of script.js. Let's walk through those. Status simply holds a reference to the paragraph tag you'll write status updates to, and video holds a reference to the HTML video element that will render the webcam feed. Next, you can grab references to all the key buttons from the HTML page. First, you have a button to enable the camera, a reset button to reset the app and start over, and a train button to begin training after data is gathered for each class. You can now define the expected input width and height for the MobileNet model. The one you'll be using expects an input image size of 224 by 224 pixels in size. By storing this in a constant near the top of the file like this, if you decide to use a different version later, it makes it easier to update the values once instead of having to replace it in many different places. Next, a constant called stopDataGather is defined and set to -1. Essentially, this stores a state value so you know when the user has stopped clicking a button to gather data from the webcam feed. By giving this a more meaningful name like this, it'll make the code much more readable later on when you use it. Finally, you've got an array lookup called class names that holds the human readable names of the possible class predictions. This will be populated later. Okay, now that you've got references to the key elements, it's time to associate some event listeners to them. Start by adding click event handlers to key buttons. First, the enable cam button. It will call the enable cam function when clicked. Second, the train button that will call train and predict when clicked. And finally, the reset button that will call reset when clicked. These function skeletons are added at the end of this code to avoid errors and will be filled out later in the code lab. Next, you can find all buttons that have a class of data collector using document.querySelectorAll. This will return an array of elements found from the document that match. You can then iterate through the found buttons and associate 2 event listeners for each, one for mouse down and one for mouse up. This allows you to keep recording samples as long as the button is pressed, until the mouse button is no longer pressed, which will be useful for data collection. Both events will call a gatherDataForClass function that you'll define later. At this point, you can also push the human-readable class names from the HTML button attribute data-name to the class names array. Now, by using a class to find buttons here and not hard-coding a fixed number of data collector buttons, it allows you to change your HTML later to add more buttons, and the code will still function correctly for 3, 4, or any number of buttons like this. Next, add some variables to store key things that will be used later on. Let's walk through those. First, you've got a variable to store the loaded MobileNet model. Initially, set this to undefined. Next, you have a variable called gatherDataState. If a data collector button is pressed, this will change to be the onehotID of that button instead, as defined in the HTML, so you know what class of data you're collecting in that moment. Initially, set it to stop data gather, so the data gather loop that you'll define later will not gather any data when no buttons are being pressed. Video playing allows you to keep track if the webcam stream is successfully loaded and playing such that you can use it. Initially, this is set to false, as the webcam is not on until you press the Enable Cam button. Next, define two arrays, one for training data inputs and one for outputs. These will store the gathered training data values as you click the data collector buttons. Now, one more array is defined to keep track of how many examples are contained for each class once you start adding them. And finally, you've got a variable called predict that will control your prediction loop. This is set to false initially, and no predictions will take place until this is set to true later on. Now head on to step 9 of the code lab. Alright, all the key variables have been defined. Let's go and load the pre-chopped up MobileNet v3 model that will provide an image feature vector instead of classifications. First, define a new function called loadMobileNetFeatureModel as shown. This must be an async function, as the act of loading a model is asynchronous. Next, you can define the URL that the model you want to load is located at from the TF-Hub documentation as shown. You can then actually load the model using await tf.loadGraphModel, remembering to set the special property from TF-Hub to true as you are loading a model from this Google website. Remember, this is a special case only when using models hosted on TF-Hub. Once loading is complete, you can set the status elements in a text with a message so you can visually see it's loaded correctly and you're ready to start gathering data. The only thing left to do now is to warm up the model. With larger models like this, the first time you use the model, it can take a moment to set everything up. Therefore, it's wise to pass zeros through the model once before you start using it elsewhere to avoid any waiting in the future when timing might be more critical. You can use tf.zeros with a batch size of 1 and a height and a width of the correct size that you defined in your constants. And finally, the color channels, which in this case is 3, as the model expects RGB images. You can then log the resulting shape of a tensor returned using answer.shape to help you understand the size of the image features this model produces. Finally, you can immediately call this created function to get the loading underway. If you view your live preview right now, after a few moments, you'll see the status text change from awaiting tfjs.load to become MobileNet v3 loaded successfully as shown. Ensure this works before continuing. You can also check the console output that would have printed the size of the output features that this model produces. After running zeros through the MobileNet model, you'll see a shape of 1024 printed. As the first item is just the batch size of 1, you can see it actually returns 1024 features that can then hopefully be used to help you classify new objects. Now head on to step 10 of the code lab. Okay, now it's time to start defining your model head, which is essentially a very minimal multi-layer perceptron. Start by defining a tf.sequential model to which you'll add layers to. Next, add a dense layer as the input layer to this model. This will have an input shape of 1024 as the outputs from the MobileNet v3 model features layer are of this size, as you saw in the previous step after passing zeros for it. This layer will have 128 neurons and use the ReLU activation function. If you're new to activation functions and model layers, consider taking the course detailed at the start of this workshop to understand what these properties do behind the scenes. Now you can add the output layer. Here, the number of neurons should equal the number of classes you're trying to predict. To do that, you can use classnames.length to find how many classes you're planning to classify, which is equal to the number of buttons found at the start of your code. As this is a classification problem, you'll use the softmax activation on this output layer, which must be used when trying to create a model to solve classification problems. At this point, you can print the model summary to the console to ensure everything is looking as expected. And finally, you can compile the model so it's ready to be trained. Here, the optimizer is set to Adam, and the loss will be either binary cross-entropy if the class names.length is equal to 2, else it will be categorical cross-entropy if there are 3 or more classes to classify. Accuracy metrics can also be requested so they can be monitored in the logs later for debugging purposes. At this point, if you check your console output, you'll see the following printed. Note that this has over 130,000 trainable parameters, but as this is just a simple dense layer of regular neurons, it will train pretty fast. Now you could try changing the number of neurons in the first layer to see how low you can make it while still getting decent performance. I'll leave that for you as an activity to do once you complete the project. Often, with machine learning, there's some level of trial and error to find the optimal parameter values that you give to the model for the best trade-off between resource usage and speed. Now head on to step 11 of the code lab. Alright, next you can create a function to check if the browser supports getUserMedia by checking the browser's APIs that are available. Once defined, you can flesh out the enableCam function. First check if getUserMedia is supported using the function you just defined above. If it isn't, you can print a warning to the console. Next, define some constraints for your getUserMedia call. In this case, you also specify that you prefer the width of the video to be 640 and the height to be 480 pixels. Why? Well, there's not much point getting a video larger than this, as you'll need to be resizing this to 224 by 224 anyhow to be fed into the MobileNet model, so you may as well save some computing resources by requesting a smaller resolution. Most cameras support a resolution of this size. You can then call navigator.mediadevices.getUserMedia with the constraints above, and then wait for the stream to be returned, at which point you can get your video element to play the stream and add an event listener for the stream load. In this instance, once the stream loads, you can set video playing to true and remove the enableCam button to prevent it from being clicked again by setting its class to be removed. If you run the code at this point and click the Enable Camera button and allow access to the webcam if it's your first time, you should then see yourself rendered to the video element on the page as shown. Okay, now it's time to add a function to deal with the data collector button clicks. Head on to step 12 of the code lab. Define a new function called gatherDataForClass as shown, which is what you assigned as your event handler function at the start of this lesson. You can now check the data-1hot attribute on the currently clicked button by calling this.getAttribute with the attribute's name, in this case data-1hot as the parameter. As this is a string, you can use parseInt to cast it to an integer and assign this result to a variable named class number. Now you can set the gatherDataState accordingly. If the current gatherDataState is equal to stopDataGather, which you set to be -1, that means you're not currently gathering any data, and this was a mouse down event that fired. Therefore, you want to set the gatherDataState to be the class number you just found from the button attribute. Otherwise, it means you are currently already gathering data, and the event that fired must have been a mouse up event, meaning that you now want to stop gathering data for that class, so you can just set it back to be the stopDataGatherState, which will end the data gathering loop that you'll define shortly. Finally, you can kick off the data gather loop that will actually perform the recording of class data. Alright, so let's head on to step 13 to see how to do that. Naturally, now it's time to define the data gather loop function. This function is responsible for sampling images from the webcam video, passing them through the MobileNet model, and capturing the outputs of that model, which is the 1024 feature vectors. It will then store them along with the gatherDataState ID of the button that is currently being pressed, so you know what class these feature vectors represent. Let's walk through it. First off, you're only going to continue if video playing is true, meaning that the webcam is active and gatherDataState is not equal to stopDataGather, meaning a button for class data gathering is currently being pressed. Next, wrap your code in a tf.tidy to dispose of any created tensors in the code that follows efficiently. The result of this tf.tidy code execution will be stored in a variable called imageFeatures. Now you can grab a frame of the webcam video using tf.browser.fromPixels. The resulting tensor containing the image data will be stored in a variable called video frame as tensor. Next, you can resize the video frame as tensor variable to be of the correct shape for the MobileNet's input. Here you can use a tf.image.resizeByLinear call with the tensor you want to reshape as the first parameter, and then a shape that defines the new height and width you require, which are defined by the constants you already created at the start of this lesson. Finally, set align corners to true in the third parameter to avoid any alignment issues when resizing. The result of this resize is stored in a variable called resizeTensorFrame. Clearly, this will stretch the image as your webcam image is 640 by 480 pixels in size and the model needs a square image of 224 by 224 pixels. For the purpose of this demo, this should work fine. However, once you complete this lesson, you might want to try and crop a square from the image instead for even better results for any production system you might create. Next, you must normalize the image data. Image data is always in the range of 0 to 255 when using tf.browser.fromPixels. That means, in this case, you can simply divide resizeTensorFrame by 255 to ensure all values are between 0 and 1 instead, which is what the MobileNet model expects as inputs. Finally, you can push this normalized tensor through MobileNet by calling MobileNet.predict, to which you pass the expanded version of the normalized tensor frame using expanddims, so it becomes a batch of 1 as the model expects a batch of inputs for processing. Once the result comes back, you can then immediately call squeeze on that to squash it back down to a 1D tensor, which then return and assign to image features that captures the result from tf.tidy. Now that you've got the image features from MobileNet, you can record them by pushing them onto your training data inputs array that you previously defined. In a similar fashion, you can also record what this input represents by pushing the current gathered data state to the training data outputs array too. Note here that the gatherDataState variable would have been set to the current class's numerical ID that you're recording data for when the button was clicked in the previously defined gatherDataForClass function. At this point, you can also increment the number of examples you have for a given class. To do this, first check if the index within the examples count array has been initialized before or not. If it's undefined, you can simply set it to 0 to initialize the counter for a given class's numerical ID. You can then simply increment the examples count for the current gatherDataState. Finally, you can update the status text on the web page to show the current counts for each class as they're captured. To do this, you can just loop through the class names array and then print the human readable name combined with the data count at the same index in examples count. Last but not least, call window.requestAnimationFrame with dataGatherLoop passed as a parameter to recursively call this function all over again. This will continue to sample frames from the video until the button mouse up is detected and gatherDataState becomes stop_dataGather, at which point the dataGather loop will end. Okay, if you run your code at this point, you should be able to click the Enable Camera button, await the webcam to load, and then click and hold each of the Gather Data buttons to gather examples for each class. Here you can see me gather data for my mobile phone and my hand respectively. You should then see the status text updated accordingly as it stores the tensors in memory as shown on this slide. Okay, now head on to step 14 of the code lab. The next step is to implement your train and predict function, which is where the transfer learning actually takes place. First, ensure you stop any current predictions from taking place by setting predict to false. Next, shuffle your input and output arrays to ensure order does not cause any issues in training. Now you can convert your outputs array to be a tensor 1D of type int32 so it's ready to be used in a one-hot encoding. This is stored in a variable named outputs as tensor. You can then use the tf.oneHot function with its outputs as tensor variable along with the max number of classes to encode, which is just the class names.length. Your one-hot encoded outputs are now stored in a new tensor called one-hot outputs. Now currently, training data inputs is an array of tensors. In order to use these for training, you'll need to convert the array of tensors to become a regular 2D tensor. To do that, there's a neat function within the TensorFlow.js library called tf.stack, which, as you may have guessed, takes an array of tensors and stacks them together to produce a tensor as an output instead. In this case, a tensor 2D is returned, which is what you need for training a batch of one-dimensional inputs that are each 1024 in length, containing the features recorded. Next, you can await model.fit to train the model. Here, you can now pass your inputs as tensor variable along with the one-hot outputs. And in the configuration object, set shuffle to true, use a batch size of 5 with 10 epochs, and of course specify a callback for onEpochEnd to the log progress function that's defined at the end. Finally, in this function, you can dispose of the created tensors as the model is now trained. You can then set predict back to true to allow predictions to take place again, and then call the predict loop function to start predicting live webcam images. Now at this point, you can also define the log process function to log the state of the training, which is used in model.fit above that will print results to the console after each round of training. Alright, you're almost there. Time to add the predict loop function to make predictions. First, check that predict is true so that predictions are only made after the model is trained and available to use. Next, you can get the image features for the current image just like you did in the data gather loop function. Essentially, you grab a frame from the webcam using tf.browser.fromPixels, normalize it, resize it to be 224 by 224 pixels in size, and then pass that data through the MobileNet model to get the resulting image features. Now, however, you can use your newly trained model head to actually perform a prediction by passing the resulting image features just found through the newly trained model head's predict function. You can then squeeze the resulting tensor to make it one-dimensional again and assign it to a variable called prediction. With this prediction, you can find the index that has the highest value using argmax and then converting this resulting tensor to an array using arraysync. This value is stored in the variable called highestIndex. Next, you can also get the actual prediction confidence scores in the same manner by calling arraysync on that tensor directly too. You now have everything you need to update the status text with the predictions. To get the human readable string for the class, you can just look up the highest index in the class names array and then grab the confidence value from the prediction array in the same manner. To make it more readable, as a percentage, just multiply by 100 and math.floor the result. Finally, you can use window.requestAnimationFrame to call prediction loop all over again once ready to get real-time classification on your video stream. This will continue until predict is set to false if you choose to train a new model with new data. Which brings you to the final piece of the puzzle, implementing the reset button. Head on to step 15 of the code lab. First, stop any running prediction loops by setting predict to false. Next, you can delete all contents in the example's count array by setting its length to 0, which is a handy way to clear all contents from an array. Now go through all the current recorded training data inputs and ensure you dispose of each tensor contained within it to free up memory again, as tensors are not cleaned up by the JavaScript garbage collector. Now you can safely set the array length to 0 on both the training data inputs and training data outputs arrays to clear those too. And note that if you had set the length to 0 on training data inputs before disposing the tensors would be unreachable but still in memory and not disposed of, which would be very bad as this would cause a memory leak. Finally, set the status text to something sensible and print out the tensors left in memory as a sanity check. It should be noted that there'll be a few hundred tensors still in memory, as both the MobileNet model and the multi-layer perceptron you defined are not disposed of, as you'll need to reuse them with new training data if you decide to train again after this reset. Alright, now head on to step 16 of the code lab. Okay, now it's time to test out your very own version of Teachable Machine. Head to the live preview, enable the webcam, gather at least 30 samples for class 1 for some object in your room, and then do the same for class 2 for a different object. Hit train and check the console log to see progress. It should train pretty fast, and once trained, show the object to the camera to get live predictions that will be printed to the status text area on the web page near the top. If you're having trouble, check my completed working code on the link shown to see if you missed copying over anything. Finally, head on to step 17 of the code lab. Congratulations! You just completed your very first transfer learning example using TensorFlow.js live in the browser. Remember to try it out and test it on a variety of objects. You may notice some things are harder to recognize than others, especially if they're similar to something else. You might need to add more classes of data or more training data to be able to tell them apart. Now, in this code lab, you learnt what transfer learning is and its advantages over training a full model from scratch. You also now know how to obtain models for reuse from TensorFlow Hub, and how to set up a web app suitable for transfer learning. You also learnt how to load and use a base model to generate image features, and then how to train a new prediction head that can recognize custom objects from webcam imagery, which was then used to classify data in real time. If you're new to TensorFlow.js and want to understand deeper what some of the options and terminology in this workshop represent, you may want to consider taking my Zero to Hero course that assumes no prior knowledge in machine learning and will teach you everything from a blank canvas, as this workshop was aimed at intermediate users of the TensorFlow.js library who are already familiar with tensors and our APIs. But now, with these superpowers, you can recognize any object you wish in your own web apps. And what problems in your life could you use this for? Maybe you can launch a video when you recognize a brand's new product. Or maybe you can recognize when your car is in front of the garage and use a Raspberry Pi to open the door automatically. The possibilities are endless. If you make something using TensorFlow.js, be sure to tag it with the hashtag MadeWithTFJS on social so we can find your work for a chance to be featured on the TensorFlow YouTube channel. Thanks for listening, and I'll see you next time.
Oke, tadi di awal itu ada dikasih link buat ke course-nya. Jadi tadi ada course-nya kalau ada yang... Nah, yang ini ya. Google 3KML 5PM. Aku udah sempat coba juga untuk course ini. Aku kirim linknya. Oke, ini ya, course-nya ini. Jadi kalau kita mau ambil yang course ini free, kita cuma bisa dapat materinya aja, tapi nggak dapat sertifikatnya gitu. Tapi kalau yang mau berbayar ada lagi gitu ya. Ini komplit juga, ini boleh banget kalau mau belajar, kalau mau ambil free juga lumayan, udah dapat materinya banyak banget gitu. Ya, ini bisa dieksplor nanti kalau memang mau ambil. Jadi di sini instrukturnya langsung si Jason-nya itu ya. Nih, Jason Mies. Jadi instrukturnya langsung Jason Mies ini. Tuh. Oke. Sampai di sini mungkin ada yang mau tanya. Tadi dari videonya itu udah dijelasin 17 ini langsung semuanya. Jadi kalau masih kurang paham bisa nonton, bisa baca sendiri juga dari sini. Kopas-kopas code-nya bisa langsung dari sini gitu. Oke, sampai di sini ada yang mau bertanya mungkin? Untuk materi browser based model cuman sampai di situ, jadi mungkin ada yang mau bertanya atau mau tanya tentang materi yang kemarin, atau memang masih ada yang belum bisa buat cara-cara bukanya kayak yang kemarin. Pakai TensorFlow browser based model paling mudah, yang Kakak bikin dulu apa project apa? Aku kalau untuk yang project langsung gitu belum pernah sih pakai yang browser based model ini. Kalau untuk yang project langsung, yang project yang dikerjain gitu nggak pernah sih. Cuman kayak contoh-contoh, terus ngerjain cuman buat dapat sertifikat gitu, itu aku ngerjain. Tapi kalau untuk project nggak sih, aku belum pernah. Karena aku nggak gitu familiar juga sebenarnya sama JavaScript, Node.js, aku nggak begitu familiar gitu. Yang kemarin mungkin masih ada yang bingung cara buka web servernya. Kok kelihatannya ribet semua proyeknya? Iya, ribet. Sertifikasi TensorFlow nanti bikin browser based model dari nol berarti kan ya Kak? Enggak sih, kalau yang sertifikasi TensorFlow itu nanti ada 5 soal. Jadi ada 5 soal itu, aku yang browser based itu nggak ada deh. Itu kayak CNN, NLP, time series, gitu-gitu sih. Terus kalau TensorFlow itu nanti kita codingnya itu di PyCharm. Link video YouTube-nya ada di PPT ya, nanti aku share. Apakah ada link course gratis untuk memahami atau mendalami TensorFlow tapi dapat sertifikat? Kalau yang untuk dapat sertifikat itu setahu aku pada bayar gitu. Kalau mau coba Coursera itu dapat gratis cuman 1 minggu kalau nggak salah ya. Ya DTS. Kalau untuk yang online course pasti bayar. DTS, oke. Kayak yang tadi itu, yang link yang tadi ini juga kalau cuman dapat materinya aja gitu, cuman buat belajar aja tapi nggak dapat contoh coding yang buat tugas-tugas gitu, itu gratis. Tapi kalau mau sampai bisa akses codingannya, bisa akses contoh soal codingnya gitu, itu harus bayar subscription. Kayak Coursera itu juga bayar. Kalau Indo itu ada nggak ya? Yang ini kayaknya belum ada sih. Online course Indo yang tentang bahas semua kayak TensorFlow itu kayaknya belum ada sih. Yang bahas machine learning online course Indo dan itu pakai bahasa Indonesia itu di coding itu juga, tapi itu juga bayar kelasnya. Ya bisa AI, ya bisa AI. Itu ada. Coursera bisa ngajuin, iya betul bisa ngajuin. Tapi kayaknya ada waktunya gitu, seminggu atau berapa ya? Cuma 14 hari ya kayaknya. Kalau penasaran tentang yang sertifikasi TensorFlow, itu sebenarnya banyak udah di-share orang-orang tentang sertifikasi TensorFlow di Medium gitu. Itu udah banyak yang udah share pengalamannya ngerjain sertifikasi TensorFlow. Tuh kalau ngerjain sertifikasi TensorFlow tuh waktunya 5 jam. Kalau Coursera tuh juga ada yang bisa buat akses semua kelas gitu ya. Itu Coursera Plus kalau nggak salah. Itu bisa buat akses semua kelas. Oke, mungkin ada lagi. Kalau enggak, mungkin aku sambil share. Besok kita buka sesi, instruktur buka sesi untuk Q&A kembali. Itu jam 11, nanti aku umumin lagi di Discord juga. Terus untuk yang memang belum ngisi buat dataset, itu masih bisa buat diisi ya. Info dataset. Hari ini terakhir buat pengisian formnya ya. Jadi yang nyusul itu tetap waktu pengumpulannya sama ya. Jadi cuma dapat waktu ngerjain seminggu gitu. Ini masih bisa dibuka linknya. Oke, boleh Pak buat fitur seleksi pakai sklearn. Kalau kemarin dari mekanisme itu cuman harus ada TensorFlow aja. Kalau mau ditambah-tambah yang lain itu nggak masalah. Yang penting harus ada TensorFlow-nya juga. Terus boleh pakai transfer learning. Terus boleh tambah dataset juga. Dan nggak boleh pakai API. Kalau nggak nyangkup yang itu sih aman kok, boleh aja. Oke, untuk proposal itu udah di-upload ya kemarin. Jadi udah dikasih link template untuk proposal dan link template untuk PPT. Nah, ini ya contoh template-nya. Yang atas ini cover-nya ya, nanti isinya baru di halaman selanjutnya gitu. Terus untuk link PPT, kayak gini, dan yang lainnya menyesuaikan dengan pertanyaan yang ada di, yang perlu dijawab di mekanisme ini ya. Untuk ada perkenalan, ada pembagian tugasnya gimana, penjelasan datasetnya, apa yang dikerjakan, apa hasilnya, apa hasil penelitian dan komparasi yang telah dilakukan, dan penutup. Untuk permasalahan dari tema topiknya itu mengikuti dari deskripsi dari dataset atau harus dicari lagi tema topik permasalahannya. Oke, kalau ada yang pakai dataset tambahan, itu kan pasti topik permasalahannya akan beda ya. Kayak mungkin yang dicari itu beda lagi gitu. Nggak sesuai sama deskripsi dari datasetnya. Nah, itu disesuaikan aja sama yang dikerjain gitu. Link mekanisme ini, bentar, kayaknya ada yang udah dibentuk Bitly. Ya, bit.ly/mekanisme.ml. Untuk di proposal, apakah perlu dicantumkan algoritma yang dipakai nanti, Kak? Oke, mungkin ini aku bold. Biar kelihatan jelas ya ininya. Oke, untuk algoritmanya itu mungkin bisa di yang project reference. Jadi kan kayak makalah, jurnal, artikel itu kan nanti ada algoritma apa gitu ya yang dipakai berdasarkan ada makalah, jurnal, dan lain-lainnya gitu. Itu mungkin bisa dilihat juga di situ. Terus untuk yang mau pakai project apa, kalau udah ada kayak jurnal yang dipakai gitu ya. Terus kalau projectnya misal kita mau nyebutin aja pakai algoritma apa gitu, ditulis di executive summary. Cuman disebutin aja pakai algoritma, misal peringkasan kata, pakai algoritma length. Nah, langsung kayak gitu aja. Terus project scope, ini garis besar, batasan proyek, project schedule, ini pakai Gantt. Oke, kalau seandainya di tengah jalan ada perubahan algoritma namun proposal sudah dikirim, apakah diperbolehkan? Nanti kan ada 2 kali nih pengumpulannya. Yang pertama kan dari proposal ini, yang kedua kan dari video yang dikumpulin. Video durasi 10 menit. Kalau memang nantinya ada perubahan di saat mengumpulin kan kita tetap dapat gitu ya, kayak dokumentasinya apa, video presentasinya gimana, dan code yang ada di GitHub itu kan kita tetap tahu ya. Dari itu ada yang berubah apa gitu. Jadi nggak masalah sih ya, harusnya untuk yang itu. Cuman jangan terlalu jauh aja ya berubahnya. Oke, ini kayaknya belum ada yang kayak penjelasan itu ya. Videonya boleh dijelaskan oleh satu orang aja. Videonya dijelaskan oleh orang yang mengerjakan langsung gitu. Jadi biar kita juga tahu siapa aja bagian yang ngerjain. Kalau yang berubah kan ini algoritmanya aja ya. Tapi kan yang di topik yang dikerjain masih sama gitu. Misal kayak ringkas kata gitu, tetap masih ringkas kata, nggak kayak yang berubah jauh banget gitu ringkas. Ya, nggak boleh yang kejauhan banget gitu. Kalau untuk caranya itu kan bisa beda-beda, nggak apa-apa sih. Bisa berubah nanti kayak ada pertimbangan lain, misal akurasinya kurang atau yang lainnya nggak apa-apa. Setelah dicoba ternyata akurasinya ada yang nggak bagus gitu, itu boleh sih. Ini mungkin nanti aku tambah lagi ya, kayak ini masih ada yang kurang. Ini baru peraturan di mode sama checklist pengumpulan. Mungkin nanti ini aku tambahin buat yang kemarin disebutin waktu di Q&A yang kayak nggak boleh pakai API, nggak boleh. Yang itu kan belum ada ya. Itu nanti aku tambahin di sini. Pengumpulan proposal kemana ya? Pengumpulan proposal masih di 16 Juli. Nanti kita buka baru di 14 Juli. Form pengumpulannya. Untuk project scope dan deliverable, nanti dijelaskan di project scope ini lebih ke batasan masalah dari implementasi projectnya, Kak. Kemudian task-tasknya nanti dijelaskan di sana, Kak. Oke, yang ini ya. Ya, ini dijelasin semua batasannya apa. Terus habis itu kan juga cakupan terperinci yang itu ya. Tugasnya kita task-tasknya apa sih juga di sini. Nah, ini ada nih, tiap mingguan juga bisa diterima, jadi ada task-tasknya gitu ya. Ini nanti aku tambahin di sini buat ketentuan yang tadi, yang kemarin cuma disebutin lisan itu. Terus ini udah jelas ya kalau untuk yang proposal template-nya. Nanti bisa dataset yang digunakan sama termasuk dataset tambahan gitu ya. Untuk reference nggak perlu sampai ikut kayak gitu, jadi tinggal dataset itu pakai apa, terus maka jurnal itu tinggal dari namanya, judul sama pengarangnya, judul, tahun, perlu sampai publisher dan yang lainnya. Nanti sama linknya boleh, link juga boleh. Di sini gimana nih? Ada yang kelompoknya cuma sendiri gitu, Masian. Ada yang belum ketemu kelompok sama sekali mungkin. Ada, oke. Kalau masih sendiri berarti bakalan solo player dong. Ada 61 tapi hilang-hilangan. Oke, semangat ya. Ini belum semua masukin link nih. Mungkin kalau ada yang dari kelompoknya ini boleh dikirim di chat. Aku tambahin. Ini ada 2 nih. Kalau ada ngisi yang pertama, yang kedua nggak harus isi lagi kan kelompoknya ya. Kalau udah dapat kelompok nggak perlu isi lagi sih. Buat yang form dataset kan. Saya dapat agree. Itu ada beberapa file CSV tentang produk pertanian. Apakah harus dipakai semua atau cuma pilih salah satu? Bebas ya, itu boleh. Misal cuman yang mau dipakai satu. Misal kan kemarin ada kayak jagung, singkong gitu ya. Jagung dan yang lainnya gitu ya. Itu kalau misal cuman mau ke lihatnya yang jagung doang, itu nggak apa-apa. Kalau mau lihat keseluruhan juga nggak apa-apa gitu. Ini tuh yang paling sedikit itu yang communication. Cuma 2 orang, 2 kelompok. Ini bisa sih dari sini langsung. Oke. Ada lagi mungkin? Oke. Besok kita bakal pakai Zoom kelas B ya buat pertemuan Q&A kayak minggu lalu. Kita pakai Zoom kelas B. Oh, besok tanggal 9 Juli. Oke, mungkin ini besok ya. Ini besok juga aku share linknya semua sama aku share recordingnya juga di kelas. Oke, udah jam 21.52 ini. Kalau masih ada yang mau bertanya boleh. Atau kita akhirin kelas hari ini. Ini aku kasih tambahan ya di sini. Biar semua juga tahu kalau kapan diupdate gitu ya. Oke, mungkin ada lagi? Kalau enggak, aku izin buat stop share screen. Oke. Mungkin yang bisa open cam, boleh open cam. Tunggu sampai jam 21.55 ya. Oke, aku mulai dari layar pertama. Oke, layar kedua. Oke, Taufik Ohan. Kak mau konfirmasi lebih jelas lagi untuk API ini. Apakah penggunaan pre-training masuk penggunaan API kan? Bukan termasuk penggunaan API kan, Pak? Kalau pre-training kan kayak transfer learning ya. Transfer learning tuh diizinin sih. Kalau yang nggak boleh yang langsung API itu yang kayak kemarin juga udah dijelasin ya waktu Q&A itu kayak langsung tinggal panggil aja langsung udah selesai gitu. Tanpa coding apapun lagi. Tuh. Mungkin nanti aku juga perjelas ya yang tentang API yang lainnya itu aku perjelas di mekanisme gitu ya. Oke. Iya, yang tanpa konfigurasi lagi, yang tanpa fine tuning lagi. Jadi yang emang langsung tinggal dipakai gitu. Kalau transfer learning masih diizinin kok. Oke, kalau gitu kita akhirin kelas hari ini. Makasih buat semuanya yang udah datang. Kita ketemu lagi besok Senin. Terima kasih semuanya. Selamat malam.